Section 9.5, Alternating Series. An alternating series is one whose terms alternate between positive and negative, such as 1 minus a half plus a fourth minus 1/8, etc., which would be the series as n goes from 1 to infinity of -1 to the n minus 1 times 1 over 2 to the n minus 1. Now, the alternating series test enables us to claim convergence anytime the series satisfies three conditions. First of all, we must have an alternating series with the nth term positive. So it must be of this form. So we have -1 to the n or -1 to the n minus 1. And these series will converge provided both of these conditions are met. That the limit as n goes to infinity of the nth term is 0, and that the n plus 1th term, which is positive, is less than or equal to the nth term. In other words, the next term without the negative sign, just the next term in the sequence, is less than the previous term. So the n plus 1th term has to be smaller than the nth term. Another way to think about this is that if a series is alternating, if the absolute values of its terms form a decreasing sequence, and if the limit of these absolute values is 0, then the series is convergent. In other words, if we have this series as n goes from 1 to infinity, -1 to the n minus 1 times a sub n, that would give us, when n is 1, that would make our term positive, a1. When n is 2, that would make the next term negative. When n is 3, that would make the next term positive. So we can see we have alternating signs on the terms. So we have an alternating series. And here's the three conditions. A sub n is positive for all n. The n plus 1th term is less than the nth term. And the limit as n goes to infinity of a sub n is 0. I would ask you to please listen to the explanations of the problems, and then at a particular time, I will have you pause the video to write down the work. So let's look at, first of all, what is our nth term? It is n over 2n minus 1. Okay, we know that that is positive for all values of n. Now we're going to take the limit. Notice that when applying the alternating series test, the limit is not taken on the -1 to the n or n plus 1 factor. Okay, so when I take the limit, I'm just taking the limit of the nth term. And that limit is 1/2, which is not 0. So this diverges by the alternating series test. We don't need to check this condition since this one's not met. All three conditions have to be met. The nth term positive, the limit of the nth term 0, and the n plus 1th term less than the nth term. Number 2, as n goes from 1 to infinity, -1 to the n times n over natural log of 2n. All right, when you see this, by the way, that is understood to be natural log of the quantity 2n. Okay. Well, first of all, we know that our nth term is positive. So now let's look at the limit as n goes to infinity of n over natural log of 2n. Well, the problem here is we have indeterminate form. The limit as n goes to infinity is infinity. The limit as n goes to infinity of natural log of 2n is infinity. So we have indeterminate form, which means L'Hopital's rule applies. Since L'Hopital's rule applies, we can take the derivative of n, which is 1, and the derivative of natural log of 2n, which is 2 over 2n, which is 1 over n. So we have the limit as n goes to infinity of 1 over n. Now 1 over n is n. And as n goes to infinity, this goes to infinity, which is not 0. So again, we diverge by the alternating series test. you should state at the beginning that we do have an alternating series because of that factor of -1. So before we can think about the alternating series test, we do have to confirm we have an alternating series. With numbers 1 and 2, that was really easy because we could see that factor of -1. Let's look at what's going on here. When n is 1, I get cosine of n pi is the cosine of pi, which is -1. When n is 2, I get the cosine of 2 pi, which is 1. When n is 3, I get the cosine of 3 pi, which is -1. When n is 4, I get the cosine of 4 pi, which is 1. Okay, so we do have an alternating series. My series can be written like this, and my nth term is 1 over n. So we have an alternating series. My nth term is 1 over n, and we know that my nth term is positive. So now let's do the next part, which is, does the limit equal 0? So the limit of our nth term is 0. So our first condition is actually met. So now, is the n plus 1th term smaller than the nth term? The n plus 1th term is smaller than the nth term. Think about this. Remember, the larger the denominator of a fraction, the smaller the value of the fraction. So our next condition is met, and that is the n plus 1th term is less than the nth term. So we have an alternating series, so I can use the test. The nth term is positive, the limit of the nth term is 0, and the n plus 1th term is less than the nth term. So we can say our series converges by the alternating series test. The alternating series remainder or estimation theorem. If a convergent alternating series satisfies this condition that the n plus 1th term, which is positive, is less than or equal to the nth term, then the remainder, r sub n after n terms, involved in approximating the sum by a partial sum of n terms is less in magnitude than the first neglected term. In other words, my remainder after n terms has to equal the actual sum of the series minus the partial sum, and that is less than or equal to the n plus 1th term. Now, an alternate way to think about the alternating series remainder theorem is this. If my alternating series satisfies all three conditions of the alternating series test, then the error in the approximation using the nth partial sum is, in absolute value, no more than the absolute value of the first omitted term. In other words, when my series, alternating series, is approximated by a partial sum, then the remainder after that partial sum is the magnitude of the sum minus the partial sum, which is less than the next term. That is, the error is shorter than or less than the next term. Now, this is a really nice visual that shows what's going on. So let's start at 0. We have done no terms. Okay? And now let's do my first partial sum, the sum of one term, and that takes me all the way to here. Now, this is an alternating series, so that means when I add my next term, I'm going to go this way. And let us remember that the a sub n plus 1 must be less than a sub n. So when I come here, my next term must be smaller. But it had a negative sign in front of it, so it moved us left. Now the next term we're going to add, and we're going to go this way, but not as far as from where I was. Now we're going to subtract because of that negative one. Again, not coming as far as I was over here. Now we're going to add the next term. We're going to subtract. Do you see us converging to this sum? Notice that in my partial sums, my odd sums are decreasing towards this sum, and my even sums, even term sums, are increasing towards that sum. This is a concept that often shows up on the AP exam. So notice that our sum of one term was a sub 1. Our partial sum of two terms would be a sub 1 plus a sub 2, which got me here. Our partial sum of three terms would be a sub 1 plus a sub 2 plus a sub 3. So continuing in this way, we see that the sum of two terms, four terms, six terms is an increasing sequence, while the sum of one term, three terms, five terms is a decreasing sequence. But the entire sequence of partial sums converges to S, since we have a series that satisfies the conditions of the alternating series test. So the even-numbered terms of the sequence of partial sums are increasing to our actual sum, while the odd-numbered terms of the sequence of partial sums are decreasing to our sum. At each step of the way, the distance that my partial sum is away from S is less than the next term. Notice that if I'm here at 4, my partial sum at 4, here's my actual sum. But my next term is going to add it and take me over here. So this distance is less than the next term that's taking me over to this sum. In fact, we now know that at each step, whether we have an underestimate or an overestimate, that is, we know the sign of the error. When the next term in the series is positive, we have a partial sum that is too small, so the remainder is positive. When the next term of the series is negative, it is because our approximation is too big, so our remainder is negative. If the series is alternating and convergent, we can actually find the remainder. Okay, let's look at that again. We know at each step whether we have an underestimate or an overestimate. That is, we know the sign of the error. When the next term in the series is positive, so let's say we are here, and the next term is positive, so it's going to move us over here, we have a partial sum that is too small. Here I was at S2, and to go to my partial sum of x3, I had to add a positive term. And so this partial sum, is less than the actual sum. So when the next term in the series is negative, it is because our approximation is too big. So here I am at S3. To go to my partial sum of 4, I'm having to add a negative term. Notice that my partial sum of 3 terms is greater than the actual sum. Example, approximate the sum of this series, alternating series 1 over n factorial, by its first 6 terms, then find the error. Now, notice when n is odd, my exponent will be even, and my -1 to an even power will give me a positive term. When n is even, this exponent will become odd, and odd exponent on my negative will give me a negative term. It's always important to figure that out when you're looking at alternating series. So we're going to approximate it by the first 6 terms. Well, we have an alternating converging series. How do I know it's converging? We know the n plus 1th term has to be less than the nth term. Think of 1 over 5 factorial, which would certainly be smaller than 1 over 4 factorial. We know that the limit as n goes to infinity of my a sub n is 0. We know this is alternating, and we know that the nth term is positive. So we have an alternating convergent series. So now let's look at our first 6 terms. 1 over 1 factorial minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial plus 1 over 5 factorial minus 1 over 6 factorial. And we actually have to find that sum, and that's going to be approximated on our calculators. So now the question is, how far off are we? This is my partial sum. What is my actual sum of this converging series? Well, our error, according to our formula above, the magnitude of my remainder after my 6 terms is the magnitude of the sum minus the partial sum of 6 terms, and that is less than or equal to the next term. Now, let's have a little refresher on our algebra working with absolute value inequalities. Recall when we are looking at the absolute value of x less than or equal to 1, that means x is less than or equal to 1, greater than or equal to negative 1. So when I look at this right here, the absolute value of s minus my partial sum of 6 being less than or equal to my n plus 1th term, that means, according to this, that s minus s of 6 is less than or equal to this and greater than or equal to the negative of that. And if I'm solving for my actual sum, I would add my partial sum of 6 terms this way, and I would add it that way. Okay? So you need to know this. So now I've just transferred what I had over there right here, and let's use what we know. So I want to know, this is after 6 terms, what would my 7th term be? Well, this would be 1 over 7 factorial, which is 1 over 5040, which is approximately 0.0002. I need to know that for this part of the equation. So according to this process, my actual sum is my partial sum plus 0.0002. It's less than that, and it's greater than my partial sum of 6 terms minus 0.0002. And then I can actually find those values. So my actual sum has to lie between 0.63174 and 0.63934. Pretty cool. Next example, approximate this series with an error of less than 1/1000th. First of all, I can see that each term will be positive when n is odd, because that'll give me an even exponent here, and negative when n is even. My general nth term is 1 over n to the 4th. Remember, we leave out that negative. And if I list a few, let's see how many I have to list. Notice I have to get to the 6th term before I get a term that is less than 1/1000th. And if I do some work here, I can see that 1 over n to the 4th equals 1/1000th when n is 5.623. That means I need 5 terms before I get to the first term that is less than 1,000th. So my 6th term gets me an error of less than 1/1000th. Now, I can do my partial sum of 5 terms and get it on the calculator. And now I want to know about my error. My error, or my actual sum, is going to be bounded by my partial sum plus or minus 0.001. There you go. And the extension to this is the sum of the first 5 terms. What would be the bounds? What are my boundaries? Okay, take a moment and write this example down. Absolute and conditional convergence. If the series as n goes from 1 to infinity of the absolute value of my nth term converges, then the series as n goes from 1 to infinity of my nth term converges. And we say that this series is absolutely convergent if the absolute value converges. Oh, that makes sense. And we say that our series is conditionally convergent if the series converges, but the absolute value series diverges. So here's what we're going to do. We're going to apply the alternating series test. If the alternating series converges, and there are 3 possibilities. The alternating series diverges, we're done. The alternating series converges and the absolute value series diverges, then the series is said to be conditionally convergent. And if the alternating series converges and the absolute value series converges, then the series is absolutely convergent. Again, let me explain the problem before you write it down. So here's our series. We're going to first of all apply the alternating series test. We know it's alternating, okay? And the limit of the, as n goes to infinity, of 1 over n to the 1/2 is 0. We know that our n plus 1th term would be less than our nth term. So what we can say is our series is decreasing since the n plus 1th term is less than the nth term. So we know by the alternating series test, this series converges. Now let's do the next thing. We know it converges, so we know the next step we have to do. We have to look at the absolute value series. When I take the absolute value of this, that gives us this. Now, what do we know about this? It is a p-series where p is less than 1, and it diverges. So this series diverges, so we say that our series is conditionally convergent since the alternating series converges, but the absolute value series diverges. Take a moment to write this down. Example 7. We have an alternating series and we know that a sub n is positive. So let's look at the limit as n goes to infinity of 1 over 3 of n. That is certainly 0. We know that the n plus 1th term would be less than the nth term. So we have an alternating series that converges by the alternating series test. Now let's go to step 2. Let's look at the absolute value series. When I look at the absolute value, we get this series. Now, what do I know about this one? It is geometric. Absolute value of r is 1/3, which is less than 1. So this converges. So the alternating series converges. The absolute value series converges. Therefore, this series is absolutely convergent. Okay, take a moment to write down these examples. Your TPs for 9.5 are 13, 15, 31, and 47. See you next time.